Hello and welcome to Getting Started with using GNAT Pro with Wind River VxWorks 653. Let's start with some background about the ARINC 653 standard. The ARINC 653 standard addresses the problem of running different applications with different design assurance levels on shared hardware. Design assurance levels describe different levels of safety criticality for avionics certification. The DO-178C standard describes 5 levels of failure tolerance. Level E is the least critical, and a failure of a Level E system will have absolutely no effect on the safety of an aircraft. The canonical example of a Level E system is an in-flight entertainment system. Though, if an entertainment system were integrated with the crew's public address system, it might actually need to be certified to Level D instead. Failure of a Level D system would cause some relatively benign effects, such as slightly reducing the aircraft's margin of safety or slightly increasing the crew's workload. Applications involving transponders, communication, and system maintenance have been certified to Level D. Level C is a major failure condition. Failure of a Level C system would significantly reduce the safety margin or significantly increase the crew's workload. Passenger injuries become possible with a failure of a Level C system. An example of a Level C system could be an electronic flight bag that contains copies of operating manuals and navigational charts. Level B failures are considered hazardous. Failure of a Level B system can have a large impact on safety or performance, significantly stresses the crew, and could possibly cause serious or fatal injuries. The pilot's primary flight display is a good example of a device that has to be certified to Level B. The most critical is Level A. A failure of a Level A system may result in a crash of the aircraft and possibly loss of life. Flight control systems and engine control systems are examples of systems that must be certified to Level A. In the past, aircraft were built using federated systems. In other words, each functionality would be deployed using one physical box. Each box, composed of software and hardware, is certified as a complete module to a certain assurance level, and this kind of certification was relatively inexpensive. A failure of some kind of functionality would be limited to the box that function is housed in. However, the problem with this approach is the need for more hardware. More hardware means increased weight and increased power requirements. Nowadays, we develop using Integrated Modular Avionics, or IMA. Multiple applications are deployed on shared hardware using multi-programming techniques that are more rigorous than the kind most developers are used to. The ARINC 653 standard specifies requirements for platforms that host multiple independent software applications. It demands rigorous partitioning both spatially and temporally. Spatial partitioning ensures strict memory protection between applications, and this is accomplished through the use of an MMU. Temporal partitioning ensures that applications are incapable of affecting others as they vary their CPU resource usage. This is accomplished using a strict scheduler. And there are facilities for communication within and between partitions, as well as for health monitoring. So instead of having to certify the entire box and all of its contents to the same assurance level, ARINC 653 enables the certification of each application independently, even when multiple functions share the same hardware. VxWorks 653 provides components that are certifiable to DO-178C Level A. This includes a hypervisor, the certifiable partition OS, and C runtime libraries. Each partition will be certified to whatever level is required for its application. There's also an alternative non-cert partition type available that you can use to ease development. Again, the CPU time and memory used by any partition is guaranteed to not interfere with the operation of any other partition. Application developers will be spending most of their time working within a partition, and the 3 relevant components in this domain will be your partition OS, your application, and language runtime libraries. Everything in the partition will need to be certified to the design assurance level required for the application. To aid this effort, the use of a certification subset partition, or a cert partition, will ensure that you only use functionality and components that are amenable to certification. We have already installed Wind River VxWorks 653 3.1.3 on this system. Next, we'll install a cross-compiler. For this version of VxWorks 653, we need to be sure to install the compiler for VxWorks 6 certs for PowerPC rather than the compiler for VxWorks 653. This is because the VxWorks 653 version 3.x partition OS is implemented using VxWorks 6 cert inside a hypervisor-based partition. So, when invoking this toolchain, all of your commands will be prefixed using PowerPC WRS VxWorks. The previous major revision of VxWorks 653 used vthreads to implement its partition OS. If you're using VxWorks 653 version 2.x, you'll need to install GNATPro for VxWorks 653, and your command prefix will be PowerPC WRS VxWorks AE. We'll invoke the VxWorks 6 cert installer with administrative privileges to enable the Install for All Users checkbox. And then we'll install using default settings. We'll do exactly the same thing for GPS 18.2 for 64-bit Windows. And again, we'll run the installer as administrator and take all the default settings. And then, to glue Wind River Workbench together with AdaCore's tools, we'll install GNATbench. Wind River Workbench is based on Eclipse, and GNATbench is delivered as a zip file that represents an Eclipse P2 repository. So we'll use the standard Eclipse installation mechanism to install GNATbench. First, we'll need to bring up Wind River Workbench. And then, to access the installation mechanism, we'll open the Help menu and click on Install New Software. In the upper right of the Install dialog, click the Add button to call up the Add Repository dialog. Then click Archive to choose our repository zip file. And now that the location field is populated, we can click OK. There are several bundles available, and it's important that we pick only the one that corresponds with our IDE. For VxWorks 3.1.3, this means Wind River Workbench 4. We'll choose that and click Next. Then, Next again. We'll agree to these license agreements. During installation, you'll have to verify the authenticity of the plugin certificate. The authority we use is our own, and it's called ACTE-CA. If you bring up details, you can compare your certificate's details with what you see here. So we'll trust this certificate and click OK to continue installation. And finally, we'll restart Workbench as suggested. To check our basic setup, let's build one of the examples that Wind River ships. When Workbench comes up, go to File, New, Example, choose VxWorks 653 Sample System, and go for the Debug Agent Apex Queuing Demonstration System. The only things we need to provide to this wizard are an arbitrary name for our demo system, which we'll call Demo, and a BSP. A few minutes later, we'll have a system that we can load onto the board with a debug agent partition and several demo application partitions. We've connected a Freescale P3041DS to our host with an Ethernet cable and a serial connection through a USB to RS-232 converter. Workbench helpfully comes with a serial terminal, which we'll configure to communicate using that converter at COM3 at 115 kilobits per second, N81. When we turn the board on, we can see its initial messages from the boot app, and we could display its boot settings. I've already configured networking on the board and the host to use a private Class C subnet. I haven't configured any network services on the host side though, which will be necessary to provide the board with an initial image. Workbench also comes with a built-in FTP and TFTP service. Configuration for this is available under Project, FTP TFTP Server. We'll use a trick that we sometimes use, which is to enter the full path to our system.elf file as an FTP user's home directory. That way, we don't need to provide any path info in the board's boot parameters. And with the @ at the bootloader prompt, the freshly built system makes it onto the board and begins running automatically. In this image, since there is a debug agent partition OS available, we can connect to the board via Ethernet and debug the demo examples that are running in the system. It could be necessary for you to right-click on a virtual machine in the debugger and direct the debugger to a file containing the VM's symbols. We'll do this for both the sender and receiver apps so that we can perform source-level debugging of these apps. So GNAT Pro for VxWorks 653 comes with an example that demonstrates how to build Ada applications in this environment. So what we'll do now is build a system that can be loaded onto our development board. The system will include 2 cert partitions that communicate with each other. Everything is wrapped together using an integration project. Documentation to accomplish this is available under Wind River Workbench's Help menu under Help Contents. Expand the GNATbench for WRS Workbench User's Guide, and click on Creating and Building a VxWorks 653-3.x Integration Project. Now, we did make some updates to this documentation, however, for the most recent release of VxWorks 653.313. This version came out after GNATbench 18.2 was finalized, so we'll go to docs.adacore.com for the latest and greatest. Look for the GNATbench for WRS Workbench User's Guide, and jump to the section for Creating and Building a VxWorks 653.3.x Integration Project. In the next few minutes, we'll be doing the following. We'll be making a copy of our demonstration sources. We'll create a VxWorks 653 integration project, along with 2 empty Partition OS projects. Then we'll add Ada applications to the 2 subpartitions. We'll make adjustments to our demo to work with the hardware that we have. We'll make our Ada development environment available for use with our sender and receiver projects. Then we'll build the system image. We'll load and run the system image on our embedded board. And finally, we'll debug the system that is running on our embedded board. First, to simplify our next few steps, we'll create a project that does nothing but contain a copy of the AdaCore demonstration. We'll do this by going to File, New, Project, and by selecting the plain project wizard under the General category. We'll call this project Apex Raven and click Finish. An empty Apex Raven project then appears in the Project Explorer. Right-click on this project and invoke Import. Under the General category, choose File System. Using the resulting dialog's file system browser, we'll navigate to C, GNAT Pro, 18.2, Share, Examples, PowerPC WRS VxWorks, Workbench, Apex Raven, and click OK. Select the entire folder to copy all its contents into this project, and then click Finish. Now, all the files we need from AdaCore should be easily accessible from the Apex Raven Workbench project. The hardware.xml file that we ship with GNAT Pro 18.2 is incompatible with the latest release of VxWorks 653, so we'll delete our copy. A hardware.xml file that we can use will appear when we create our integration project. Creating our integration project is very easy. We'll start by going to File, New, Wind River Workbench Project. And then we'll choose VxWorks 653 3.1 as our target operating system. We'll hit Next, select Module Integration Project, hit Next, and enter a name for our project. We'll use Tutorial as our name, then hit Next again. Then we have a choice of BSPs. Our target board is a Freescale P3041DS, so the FSL P3041DS choice is the correct one for us. Now we'll add our two partition OSs. Click the Add button and name our first partition Sender. This should be an all-in-one CERT OS. Do it again for our receiver partition. Click Finish and Workbench will get busy assembling what we just specified. So now we have our project skeleton. Our demo provides configuration for the module integration project so that you don't need to do it yourself. We'll copy and paste the config subdirectory from the Apex Raven project to the tutorial project, overwriting files in case of any conflicts. According to our documentation, we need to match the serial devices that our hardware provides with the devices used by our example. If our hardware provides a UART0 poll device, we need to tell our example to use that. So, we open up the hardware.xml file and search for a string called UART0 poll. Since the string does exist in our hardware.xml file, we'll head over to the sender.xml file and update our device from UART0 to UART0 poll. We'll do the same for the receiver.xml file. Back in the hardware.xml file, we need to allow multiple references to this device. We add the attribute maxRefs and set it to unbounded. The final bit of config tweaking we need to do is to make sure that init.xml, sender.xml, and receiver.xml all contain bootapp_vt payloads rather than bootapp by itself, because bootapp vt is what is compatible with version 3.1 of VxWorks 653. In each of these files, we simply look for the presence of this string. There's a chance that the partition OSs will not automatically invoke our application using user appinit. So for both the sender and receiver kernel configurations, we'll open the kernel configuration, expand the application components section, and ensure that include user apple is selected. As we're going, we're saving all of our changes with Control S. Tabs containing an asterisk indicate unsaved changes that should be saved. Our partitions are now ready to receive our Ada applications. Each application we provide contains Ada sources in an src directory, a GNAT project file, and our entry point in a userappinit.c file. For the sender application, we'll copy these files from the Apex Raven helper project and paste them into the sender partition OS project that's associated with the tutorial integration project. It's expected that we're overwriting existing files, so we'll say yes to all when we're asked about that. We'll do the same for the receiver application as well. So now we have our module integration project, two partition OS projects, and Ada application sources copied into those partitions. Projects that you create using Workbench do not handle Ada by default, however, so we'll right-click on the sender project, then select New Other. Under the Ada category, we have an option to convert to an Ada project, which we'll select. After we click Next, we'll see that the fields have already been filled. Sender is the name of the project that we want to convert, and the sender.gpr GNAT project file we copied in is what we want to use with the AdaCore toolchain. We'll point this wizard to that file. Once we click Finish, our project will contain the appropriate gear to work with Ada sources, including a gnat.makefile file and an Ada runtime. Again, whatever we do for the sender project, we'll repeat for the receiver project. The last thing we'll do before we actually build this application is to adjust some variables that the GNAT project files use to select the correct tools and components for the build. We call these things scenario variables, and they're accessible in the Scenario Variables view. You can bring up the Scenario Variables view using Window, Show View, Other, and then navigating through Ada to get to Scenario Variables. The Scenario Variables view is also part of the Ada perspective. Let's bring that up instead. I'll cancel this out, then go to Window, Perspective, Open Perspective, Other, and then select the Ada perspective. The Scenario Variables pane becomes available downstairs, where we can set binding, platform, and runtime variables for our sender and receiver partitions. There are two mechanisms we can use to pass scenario variable settings to the project file. We'll use setEnvironment to use this value. The binding variable should be set to apex underscore VxW653-11162 underscore ZFP, platform to PowerPC WRS VxWorks, and runtime to Ravenscar Cert for both the sender and receiver projects. Now that all the pieces are in place, we can right-click on the tutorial integration project and invoke build project. Parallel builds are not a problem for us, so I'll dismiss this dialog. We'll point our FTP server to the freshly built system and reboot our board. In the console view, there's a button that brings up FTP TFTP server preferences. We can edit the home directory of the existing user and click OK. Note that by doing it this way, we don't need to change the boot settings on the board itself. Over in the serial terminal, we can see our boot app messages. After entering the @ to boot the board, our app begins to run. The sender partition periodically sends a message to the receiver partition, which outputs the data it receives. If we try to attach the debugger to the board, it'll fail because there's nothing in our loaded image that even initializes the board's Ethernet port. We can add debugging capability to our system by adding a debug agent. The way it's done with this version of VxWorks 653 is by adding a debug agent partition. This partition needs to be configured in a specific way, and it must execute on CPU core 0. Documentation for this is available via help contents. Open Wind River documentation, VxWorks 653 313, VxWorks 653 Debugging and Tools Guide 313, Debug Agent. We will follow the directions here to construct the Debug Agent Partition OS project, and then integrate the debug agent with our tutorial integration project. We'll start by going to File, New, Wind River Workbench Project, and selecting VxWorks 653 3.1 as our target operating system. We want to create a partition operating system project, so we'll select that as our build type. The name of the project isn't important, but we'll use the name that appears in the documentation, which is 653 DAPOS for 653 Debug Agent Partition Operating System. Our BSP is already set correctly, but the debug agent won't build under Assert OS. So instead, for this project, we'll select the option to build an all-in-one non-Cert OS. Click Finish, and the project will soon appear in the Project Explorer. So far, we created a project with a name that suggests it's a debug agent project, but there's actually nothing remarkable about it yet. Our next steps will turn this vanilla project into a debug agent. We'll open up the kernel configuration for the partition OS contained in the project, then go to the Bundles tab. Here we could add the Guest OS debug agent bundle by right-clicking on it and selecting Add. There are also directions for specifying networking addressing parameters that override the networking info from the boot line, but we don't need to do that in our environment. If you want to also include the System Viewer agent so that you can use the System Viewer GUI in Workbench, you can do so by going to the Components tab and searching for System Viewer. Right-click on the component and select the Quick Include menu item to include the agent in your build. Now we can right-click on our project and select Build Project. Now that that's done, we now have an all-in-one non-cert partition that contains a partition OS with a debug agent and a system viewer agent. We can drag this project from the top level of our Project Explorer into the tutorial module integration project. To glue the tutorial build with the 653 DAPOS project build, we need to deposit a file with a .makefile extension into the tutorial's top level. We'll right-click on the tutorial project, then go to New, File. We'll call our file 653dapos.makefile and add the text that Wind River's documentation directs us to add. At this point, when we build the tutorial project, it'll also build all of its subprojects, including the debug agent that we added to it. However, it won't actually do anything because we still need to make some additional modifications to our module integration project. We need to configure a new ARINC 653 partition with a payload, and we need to reconfigure some CPU core schedules. We can adjust properties of the framework by double-clicking on the tutorial project's module configuration knob. We'll select the Partitions tab. After selecting the Partitions element, we'll click Add. We'll select Module/Partition and click OK. The name of our debug partition must be DVM, so let's enter this. We want this partition to contain our debug agent project as a payload, so next we'll click Add Project and select our 653DAPOS Partition OS project. Hit OK, then OK again, and our DVM partition now appears in the partition list. A dvm.xml file is also created and made available in the module configuration GUI. Our debug agent must occupy a schedule named debug_sched, and this schedule must be associated with CPU core 0. Our Ada example already has a schedule called init that's running on core 0, so what we'll do is we'll move our Ada example to core 1 and reserve core 0 for the debug partition. To configure core 1, we first select cores and then click the Add button to add a new core. We'll name this core 1 and specify init as our init schedule. To actually create the init schedule, we'll click Add, select Schedule, then click OK. Name the new schedule init, and now we can begin transferring items from core 0's init schedule to core 1's init schedule. First, we'll copy the BusyVB partitions duration figure from core 0 schedule, and then we'll add a line to core 1 schedule by clicking on the plus sign and transferring BusyVB's partition and duration figures. Finally, we'll go back to core 0 and click the minus sign to remove the entry from core 0's schedule. We do the same with the sender and receiver partitions. And once we're done, we're left with only the DVM partition scheduled to run on core 0. The schedule containing the debug agent partition must be named debug_sched, so we'll adjust the name of core 0 schedule and also update the initial schedule attribute for core 0. Because we're building with system viewer functionality, we need to follow Wind River's instructions for setting up a shared memory region that the DVM partition has access to. We'll expand Module, Module OS, Memory, Shared Memory, and add a line to the Shared Memory Map table. Click the plus sign at the top right of the table and configure the name to be event log, the region to be RAM, and the size to be 1 million hex. That creates the shared memory region. To connect the region with the DVM partition, we'll go to the Partitions tab, then go to DVM, Shared Memory. There is no shared memory map table here, so we'll click Add to create one, then click the plus sign to add a line to the table. Here we only need to set the name to event log and the shared memory name ref to event log as well, and we're done. The last thing we'll do is make sure that the DVM partition has access to the hardware devices it needs to function. This we do by modifying the dvm.xml file. Our debug agent partition only needs access to the board's Ethernet interface. On this board, we're using DTSEC4, so we'll copy the appropriate text from the Wind River documentation and paste it into our dvm.xml file. After a quick text reformat, we can save our changes, right-click on our tutorial project, and select Build Project. With the debug-enabled system built, we can boot our board with a new system. Next, we'll open up our target connection details to adjust it to work with our Ada example rather than with the Wind River example. The config file attribute needs to point to the debug agent.xml file from the tutorial project, so we'll clear out some of the path and browse to the appropriate file. Then we'll enter advanced settings to disable OS awareness because our example partitions are not configured to work with it. We'll click OK, then apply, and connect to our target. We'll need to provide the locations of symbol files for our VMs here, just as we did for the Wind River example. So open up Virtual Machines, right-click on Receiver, and select Symbol Files. We'll locate receiver.pos for the receiver VM and sender.pos for the sender VM. Once we do that, symbolic debugging becomes possible, including setting breakpoints and examining variables. We hope that this video of using VxWorks 653 with AdaCore's GNAT Pro was useful to you. For more support and information, all AdaCore customers already have access to the very engineers working on our products through GNAT Tracker, our web and email-based support portal. We encourage opening tickets for more than just bugs. For instance, you can ask questions about the Ada language, or you could ask for advice about integrating our tools with your processes. There is no limit to the number of tickets you may open. In addition to the support services bundled with all GNAT Pro subscriptions, we also offer training classes as well as mentorship. Mentorship is AdaCore's technology adoption service. To help your team accomplish a goal, such as porting a legacy system to a modern platform like VxWorks 653 under a deadline, you would get paired with a mentor, gain access to all necessary AdaCore tools, get the appropriate training, and also have some number of consulting visits. So if you'd like to reduce project startup time by having an AdaCore expert available to work alongside your team, we're available and ready to help you build software that matters.